In the diagram, line TS is a tangent to the circle at S. If O is the center of the circle, angle TSP equals 21 degrees and angle RQP equals 100 degrees. Find with reasons I, angle SPR, II, angle QSR. Alright, so when we look at the diagram, of course, the line TS that is from T here, this point T to S is a tangent to the circle. Now, when we say a tangent is a line. A tangent is a line that is drawn to touch a circle or even a curve at one point. So a tangent is drawn to touch a circle at a single point. Now, I want to talk about a very special circle theorem which occurs when we have tangent. Now, let us take this as my circle, and then let me draw a tangent to this circle. So I'm going to draw a line which would touch the circle at only one point. Okay, so let us call this line, let me call this line ST as okay, let me call it okay, MT, but the line touches the circle at the point S, as we see here at the point S. So within the circle, let me put in some chords. Let me put in some chords that form an inverted triangle, a triangle that is turned upside down. Now, what I'm gonna say here is that the angle found here, if say the angle here is, let me call it put, say, you know, theta degrees here. This angle is the same as the angle found here, theta degrees. And if the angle here is, say, alpha degrees, then the angle here too is alpha degrees. Now, this theorem states that the angle between a chord, that is the angle formed between a chord is a line that is drawn to touch two parts on the circumference of a circle. So if I put A, B here, you know, from A to B is a chord because there is a line that is drawn to touch two parts on the circumference of the circle. AS is also a chord because it's a line drawn to touch two parts on the circumference of a circle. The line SB or BS is also a chord because it's a line that is drawn to touch two parts on the circumference of the circle. So a chord is a line that is drawn to touch two parts on the circumference of a circle. The line MT or say ST or whatsoever here, the line down here is not a chord, it is a tangent. It's not a chord because it touches the circle at only one point. It doesn't touch it on two parts on the circumference. And when we have a line that touches the circle at only one point on the circumference, it is better called a tangent. So that is the tangent we are talking about here. But all these lines you see within the circle are called chords. And when a chord passes through the center of the circle, it is called diameter. It has a special name that we call it diameter. So back to what we're saying. We're saying that the angle between a chord and a tangent is equal to the angle in the opposite or alternate segment. Now let us try to analyze this theorem very well. Now when we say a segment is an area that is bounded by a chord and an arc. Now when you draw a circle, you see, if I draw a circle like this and I draw a chord, you know, I put a chord here, let me all right, let me put a chord maybe somewhere here. If I put a chord somewhere here, see, a chord is a line that is drawn to touch two parts on the circumference of a circle. So let me call this chord maybe AS. Okay, this is called AS. Now I have a chord. It is drawn to touch two parts on the circumference of this circle. Now when I draw a line to touch one part of this circle, that is when I draw a tangent to this line at a point S. If I draw a line such that the line touches the circle at the point S, and that line makes an angle with this chord. Now this chord, that is a chord. In here is a chord, and outside here is a tangent. Now if I put an angle here, let me say the angle is 70 degrees here. Now that is an angle between a tangent and a chord. So let's go back to the rule. We are saying that the angle between a chord and a tangent. So you can see that that is what I'm referring to here. That is the angle between a chord and a tangent, and that is the same law that you see here. The angle between this chord AS and the tangent here, this angle theta degrees, right? So, and let me also say something here. The moment you draw a chord in a circle, it divides the circle into two halves. It divides it not actually into two equal halves, but I'm trying to say that it divides it into two segments. Let me put it that way. When you say halves, it means equally. No, that is not what I'm talking about. This chord AS, but when a chord passes through the center, it divides it into two halves. Okay, but this chord AS divides the circle into two segments. Now, if I shade this place, this shaded area is a segment. A segment is an area, that is the area, and it is bounded by an arc, that is this arc AS, that curved thing, and that is the chord, that straight line from A to S. So a segment is an area bounded by a chord and an arc. So that is a segment, that is the smaller segment, and that is another segment, that is the bigger segment. So we have the angle formed, you know, between this tangent and this chord, which kind of run through this segment too. So you see that the angle runs through this segment. Now the angle on the other side is what we are referring to as the opposite segment, because we have this segment and the other segment is opposite to this. So we call it the opposite or the alternate. That is when you change to the other one. So you kind of change to the other segment. So we are saying the angle formed between a chord and a tangent is equal to the angle which is formed in the opposite segment or in the alternate segment. So if we have another chord here and one from here, and we have an angle formed here, this angle is formed in the opposite segment. It's formed within the segment. So the angle formed between a chord and a tangent is equal to the angle in the opposite segment. That is a rule that we have here. That is circle theorem, one of the circle theorems here. Now let's look at how easily you can remember this theorem. Now an easy way to do this is always to try to see if you can draw 2z. Oh yes, draw 2z here. Now I always try to label my z. You know, a z has three lines: the first line, second line, and third line. I call the upper line the head, the middle line I call it the body, and the tail line I call it the leg. So and because this one faces that is what opposite to this, so it's something like we have so that is also the head. So let me also show this: the head, the body, and the leg. And what I do always is I tell my students that because this one faces that, you know, when two people face, probably they are going to kiss. So it's something like we have the male Z and the female Z. Now if we can have this diagram in the circle, then we should think of this law, that is the angle formed between a chord and a tangent equal to the angle in the opposite segment. Now let's see. Now when two people meet and, you know, they want a kiss or something, you see the heads come together. So the head kind of come together and form something, and at times their legs, you know, also come together. So we have something like that. Now what we are trying to say is that the angle formed between the head and body of the male, say if it is 70 degrees, is equal to the angle formed between, this time, the leg and the body of the female. In the same vein, the angle formed between the head and body of the female, say if it is 50 degrees, is equal to the angle formed between the body and leg of the male. Now we can draw a circle around this, and you see that it works perfectly. Look at it. If that is not drawn to scale, so the circle is not going to look nice, but we can draw a circle to touch the ends. You see, so something like this. So their legs kind of come together to form the tangent that we are talking about here. So anytime you have a tangent to a circle, try to see if you can, you know, illustrate these two Z within it, then you can know what you're talking about here. But remember that the Z has 3 lines, not 4 lines. So if you look at this diagram, if you want to draw the Z, and of course their legs, or should I say their knee, will be meeting down here. So these two lines here, or sorry, this one line will be serving as their legs. So let me see if I can illustrate what I just did down there here. I'm going to use a red for the male. You see, when I start from R to Q, that is one line, R to Q1, then Q to S 2, then I can go down here. But if you look at this angle, I know the angle 21 degrees. I want to make sure that this angle is found between the body and leg of the male, just as you saw here. The angle is found between the body and leg. So I have to be very careful in my choice of lines if I want to illustrate this. So if I want to start from here, RQ1, and come to QP2 and go to PS3, then ST4, 4 lines, but the Z has 3 lines. So my best bet is here. I have to start from Q. All right, so Q to P, that is the first line. Don't worry, the Z will not appear so nice, but you just need 3 lines. 1, so 2, and then 3. So that is the male. The male is kind of looking up, something like that. And they share the same head, so the female head will start from where the male head is. So if you look at it, they share, their head is merged together that way, like they are kissing, right? So the female, I have to start from here. So the female to go that way, 1, because they share the same head. Then I come down here, 2, that is the second, and then the third, so that is the leg. So that is the leg of the female, and that is the leg of the male. This is the leg, sorry, the body of the female, and then that is the body of the male, and their heads are merged together. So the head of the male and female are merged together as if they were kissing. So the angle formed, we know this angle 21 degrees. We are told from the question that angle TSP, that is T, this point SP, is 21 degrees, and this angle is formed between a chord, the chord SP. So the angle between a chord and a tangent is equal to the angle in the opposite segment. So when we come within here, this chord SP divides the circle into 2 segments. Now that is one segment. The moment we look at the chord SP, consider only the chord SP. Assume that we don't have anything here. This is the chord SP. So whatever is left here is the opposite segment that we are talking about. But we are not talking about what is here. We are just concerned with the chords that form these 2 Z here. So if you look at this diagram, because this angle is here 21 degrees is over here, the other angle should be located here because we have these 2. You can see the inverted triangle going that way, you see. So if here is 21 degrees, then here too is 21 degrees. So in the same vein, if we know the angle here, then we could also find the angle over here. So here is 21 degrees. If here is 21 degrees, then of course we should know the angle here, because the whole of this angle is 100 degrees. So let us start to write something down, and let's look at how this can better be solved. Okay, so the first thing that we're going to write is that we tell the examiner that the angle between a chord and a tangent is equal to the angle in the opposite segment. All right, so this implies that the angle TSP that we know here, angle TSP, is equal to the angle found here. And how do we even call this? Angle SQP, and sorry, SQP, angle SQP. All right, so and the whole of it is 21 degrees here. Okay, angle TSP equals angle SQP, that is 21 degrees there. All right, also we are told that angle RQP is equal to 100 degrees. So let us see if we can find the angle here. But we know that angle RQP is equal to, you know, angle RQP equals angle SQP as SQP plus the angle here, which is angle SQR, angle SQR. So RQP is 100, SQP is 21, then SQR we don't know. So this implies that angle SQR is equal to angle that is 100 minus 21, and then that should give us 79. So the angle here is 79 degrees. All right, so what we are finding is SPR, and SPR is this angle. I think the diagram is becoming a bit dirty, so all right, so we know this angle here. The angle here is 21, and now we know this angle too, and that is 79. All right, so let's look at, we want to find the angle SPR, this angle here. Okay, so also angles subtended by a chord in a segment, that is a particular segment on the circumference, are equal. All right, so if you look at the angle here, that is SPR, it is subtended by the chord SR, and this same chord SR forms the angle here. So we are saying that angle SPR is equal to the angle from here, SPR here, is equal to the angle from here, that is SQR, angle SQR. Yeah, and they are equal because, I mean, these two angles are formed by the same chord, that is the chord SR. So they are formed by a single chord, and they are in the same segments, and they all end on the circumference. So they are all equal to 79 degrees. So this implies that the angle SPR is equal to 79 degrees. All right, so we go on to look at the II, which says we are to find angle QSR. So what is QSR? That is QSR. So that is the angle QSR. All right, so we say once again that angles that are subtended by a chord in a segment on a circumference are equal. If you look at the angle QSR, it is formed by the chord RQ. So this same chord RQ, which forms this angle, forms the angle QPR. So angle QSR is equal to angle QPR. All right, and let's see what we have here. Do we know the angle QPR? We don't know the angle QPR here, but here is 79, and if here is 79, then here too is 79, because the chord SR forms this angle 79 at Q. This same chord SR forms the angle 79 at P. So if here is 79, here is 79, and if here is 21, then the angle here too is 21. So let us put that one also here, 21. So we have 21 over here. All right, so all these angles are equal because they are subtended or formed by a single chord. All right, so we look at the center of the circle too. It's pretty much important that we pay attention to the center of the circle. Anytime that you're dealing with circle theorems and you have been given the center of the circle, you look there too, because there is a lot that's really, or a theorem that is very important when we talk about the center of the circle. Now, if there is a circle and that is the center of the circle, and we have a line passing through the center of the circle, now that is a chord, and if the chord passes through the center of the circle, we call it the diameter. All right, and the angle subtended by the diameter of the circle on the circumference is always 90 degrees. Sorry. That is, the diameter always forms a right angle triangle. Okay, so if you look at the diagram, we have a chord passing through the center, that is the diameter is the chord SQ, and it forms an angle here. So the entire angle here has to be, I'm not drawing straight lines today, so the entire angle here has to be 90 degrees. In the same vein, the entire angle here has to be 90 degrees, because these angles are subtended by the diameter. And if we know here to be 79 degrees, then of course we can find the other half of the angle. All right, so we're saying that there is angle here. Let me write down something that so the angle subtended or formed subtended by the diameter on the circumference of a circle is 90 degrees. Okay, so this means that angle SPR plus angle QPR is equal to 90 degrees here. And where is QSR? QSR is here. So if we know the angle here, then of course it's equal to the angle here, because the angles subtended by the same chord in the same segment 2 are equal. So what we're going to write here is that angle SPR, so this implies that angle SPR plus, so the angle SPR plus the angle here, that is QPR, angle QPR is equal to 90 degrees. But we know SPR as 79 degrees. We don't know QPR, so that is the angle we are finding currently. Angle QPR is 90 minus 79, and when you subtract 79 from this, you get 11 degrees. So the angle here is 11 degrees, and this angle is formed by this chord, that is the chord RQ, this chord here. That same chord RQ comes over here to form this angle. So you can see that one chord is forming these two angles, and then when a chord subtends two angles on the circumference in the same segment, they are equal. So we say the angle QSR is equal to angle QPR, and that is because angles subtended by a chord in a segment on the circumference are equal. All right, so this implies that the angle QPR is equal to, QSR, that we find it, right? Yeah, QSR. So the angle QSR, which is equal to QPR, is equal to 11 degrees. So here we apply some circle theorems. The fact that when a chord passes through the center, that is the angle subtended by the diameter is 90 degrees.